Hey detectives, welcome back to AlgoStock. In this video, we're diving deeper into the world of regression with two powerful methods, RANSAC and Theil-Sen Regression. If you've ever struggled with those pesky outliers messing up your models, you're in the right place. Here's what you'll uncover in today's investigation. What exactly are outliers, and how do they influence our trusty linear regression? We'll explore the RANSAC algorithm, what it is, how it works step by step, and when it might be your best ally. Then, we'll look into Theil-Sen Regression and its unique approach to handling noisy data. And finally, we'll compare RANSAC and Theil-Sen with the Huber Regression we discussed earlier. If Huber Regression still seems mysterious, don't worry. I'll point you to a previous video where we uncovered its secrets, link in the description below. So, let's jump right in and solve the mystery of outlier-resistant regression together. The challenge of outliers. Before we dive into the details, let's talk about one of the biggest challenges in data analysis, outliers. Imagine you're analyzing how a person's weight is related to their height. You've collected a bunch of data points, but then you notice some people who are much taller but have a surprisingly low weight. Or maybe someone is really short but falls into the obese category. Or perhaps it was just a mistake when recording the data. Oops. These unusual scores, known as outliers, can throw off our entire analysis. They can give us a misleading picture, making it harder to find the real relationship between weight and height. Impact of outliers in linear regression. The presence of one outlier has skewed our otherwise near-perfect straight line. This is because linear regression treats each point in the same manner, thus is prone to data impurity. Thus, to get the most accurate insights, we need a methodology that can handle these outliers, something that can spot those unusual data points and make sure they don't lead us astray. We need a tool that can sift through all the clues, focusing only on the ones that matter most, while gently setting aside those misleading outliers. And that's where RANSAC and Theil-Sen Regression come into play. They're like the detectives of the regression world, ready to keep our analysis on the right track. RANSAC. So, what exactly is RANSAC? RANSAC stands for Random Sample Consensus, and it's a powerful method that helps us fit models to data while ignoring those pesky outliers. Now let's walk through how RANSAC works step by step. Step 1. RANSAC starts by randomly selecting two points from the dataset. It uses these points as the basis to create a line. Think of it like the detective picking two suspects and checking their story first. Step 2. Next, it calculates the slope and intercept of the line that goes through these 2 points. This line represents the story RANSAC is trying to verify. Step 3. After drawing the line, RANSAC measures how far each point is from this line. This distance is called the residual. Think of it as checking how closely other witnesses match the story given by the selected suspects. Step 4. Next, RANSAC takes the absolute value of these residuals. This helps us focus on how far each point is from the line, without worrying about whether it's above or below. Step 5. To decide which points are close enough to the line, RANSAC uses a threshold based on the median absolute deviation (MAD). This threshold helps the detective ignore those who don't fit the story. Step 6. Now, RANSAC finds the points that are close enough to the line. These are called inliers. It's like the detective identifying the witnesses whose statements fit the story. Step 7. RANSAC counts how many inliers fit this line. If this line has more inliers than any previous lines, it becomes the best line so far. This process repeats until RANSAC finds the line that best represents the majority of the data, ignoring outliers. After going through multiple iterations, RANSAC has finally found a pair of points that give the best fit line. This line includes 6 inliers, which means it fits the majority of our data points while ignoring those pesky outliers. Think of it like the detective solving the case by focusing on the most reliable witnesses and filtering out the misleading ones. Now we have a line that represents the true pattern in our data. Finding best fit. Now, you might think, we found our best fit line with RANSAC. Right, well, not exactly. RANSAC's real job is to identify the outliers and keep them out of the way. But to draw that perfect line through the data, RANSAC relies on another helper. Here's how it works. RANSAC identifies which points are the reliable inliers, and then linear regression comes in to fit a line through those inliers, completely ignoring any outliers. This way, we get a line that truly represents the underlying pattern, without being swayed by those extreme points. Theil-Sen Regressor. Now that we understand RANSAC, let's talk about another clever detective tool, the Theil-Sen Regressor. This method also helps us fit a line to our data, but it does so in a different way. It's like a detective who takes multiple pairs of clues and averages their interactions to get a better understanding of the case. Let's break down the steps involved in the Theil-Sen Regressor to see how it fits a line to our data. First, we need to examine all possible pairs of points in our dataset. For each pair of points, we calculate the slope of the line that connects them. It's important to avoid pairs where both x values are the same, as that would lead to a division by zero error. After we have the slopes from all pairs, we take the median slope. This median represents the most consistent slope across all possible pairs, which gives us a strong indication of the overall trend in the data. Similarly, we calculate the median intercept from our list of intercepts. This helps us determine the best y-intercept to pair with our median slope. Once we have our median slope and median intercept, we can find the best fit line using the Theil-Sen Regressor. This step is crucial because it uses the values that represent the most consistent trends in our data, ensuring that the final line we create is robust against outliers. Huber versus RANSAC versus Theil-Sen. Now that we've explored RANSAC and Theil-Sen regression, let's compare their strengths and weaknesses alongside Huber regression. Each of these methods has its own unique advantages and best use scenarios when dealing with outliers and fitting lines to data. Huber regression. Pros: robustness. Huber regression is resilient to outliers as it combines the advantages of both the least squares method and least absolute deviations. Smooth transition. It smoothly transitions between squared loss and absolute loss, making it effective in situations where the data may have outliers but also follow a general trend. Cons: complex tuning. Choosing the right parameter for the transition between the two loss functions can be tricky and requires careful consideration. Limited outlier handling. While it does handle outliers better than standard linear regression, it may still be affected by extreme outliers. Best scenario: use Huber regression when you expect a few outliers, but most data points are relatively normal, and you want a smooth estimation. RANSAC Regressor. Pros: effective outlier removal. RANSAC excels at identifying and ignoring outliers, focusing on the points that best fit the model. Flexibility. It can be applied to various model types beyond just linear regression, making it adaptable. Cons: randomness. Since it relies on random sampling, the results may vary with different runs, leading to less consistency. Requires multiple iterations. It may take longer to find the best model as it requires multiple iterations to ensure reliability. Best scenario: RANSAC is ideal when your data has a significant number of outliers, and you want a robust model fit while ignoring these noise points. Theil-Sen Regressor. Pros: robust to outliers. Theil-Sen regression calculates the median slope, making it very robust to outliers and ensuring a reliable trend estimation. Simplicity. The method is straightforward and easy to understand, making it a great choice for basic analyses. Cons: computationally intensive. It can be slower with larger datasets because it evaluates all pairs of points. Less effective with strong non-linearity. It assumes a linear relationship, so it might not perform well if the underlying data structure is nonlinear. Best scenario: Theil-Sen is perfect when you need a simple, robust approach to fitting a line, especially when you expect your data to have outliers. Thank you for sticking with us throughout this exploration of RANSAC and Theil-Sen regression. We hope you found the content helpful and informative. If you have any questions or thoughts, please leave them in the comments below. And don't forget to check out our previous video on Huber regression for more context. Until next time, keep digging into the data and happy analyzing.